Alrighty. So the plan this week is we're going to start working on 5.6. Oh, wait, wrong side. Is the mouse up there yet? Oh, there it is. Boom. Oh, that's what I was going to tell these kids. That's fine. All right. All righty. So, oh, geez, where'd it go again? Sorry, mess with me. There it is. Trying to find out where the mouse went. All right. Have you grown by much? Differential equations, growth, and decay. So today we're learning to solve differential equations. We'll be successful when we can solve differential equations involving growth and decay. All righty. So here are some sweet equations we're going to use today. Drink them in, folks. And on that note, you should just make a quick note of them. These both will show up again at some point today. But you should make a note of those because these are the two important, really, really important things from today. So I'm going to point them out and then we'll see how they show up. In a sense, one will develop and the other will just kind of like, hey, by the way, this is a thing. So give you a hot sec for those. Again, presented without context for now, but more will come with these shortly. Oh, it does go up there. Ooh, look at that. All right. So we'll hit those up again and see these in some different formats in a little while. All right, so a differential equation is an equation with one or more differentials in it. Again, you can make a note of this right now or just leave a space for it, or don't write it down and come back and write something about it later. This is mostly just information again for you. It's an equation with one or more differentials in it. So we solve differential equations by integrating, which gets rid of the differentials. So part of that process is separating variables, getting everything with an x on one side of your equation. Again, a differential is like dx or dy, or dt, d theta. Those are all differentials. So in a sense, you've been solving differentials for a long time, since beginning of chapter 4, really, when we've been doing antiderivatives. It's just the ones we're going to be doing today, we're getting rid of 2 differentials instead of 1. Even then, technically, we're getting rid of 2, but you'll see what I mean. So something I want to point out before we get into more stuff with differential equations is we can represent a differential equation, again, an equation with one or more differentials in it, using a slope field. So what we do to get a slope field is we take coordinates in a plane and plug them into the differential equation to get a slope. Then we sketch a small part of that slope at that point. We can also sketch out particular solutions to the differential equation by picking a point and just kind of following the slopes and to sketch out a thing. So I want to show you a little bit more of this differential, the slope field, what that is. It's not a terribly difficult concept, and it's popped up a couple times in your practice throughout the year. Again, it's just sprinkled in there throughout the book. There's not a particular single section about it. We'll do a little more work with slope fields later on, but I just want to point it out today. So here's an example of a slope field. Here's a differential equation. This would be dy over dx equals 2x over y. So basically what we do is we just take the coordinates of a point, plug them into this equation, and it gives us the slope at that point. But see how pretty that looks? So pretty. Now I'll show you kind of what I mean by what a slope field looks like. projector mode. And movable point, I want to change this part. Played with this part yesterday, so I know I can do this. All right. So like I have this differential equation. And again, just the way Desmos works, this is dy dx right here. Don't worry about the fact the way it's set up. It's just, see right up here. Let g of xy be equal to dy dx. As I move this point around, like if I wanted to trace out a function here, I would just put this point here, and then I'm just going to follow the slope. So follow the slope, follow the slope, follow the slope, follow the slope. And you can see the slope changes as I move, and I'm just trying to follow it the best I can. Now, if you were to, just trying to find my mouse, it all moved on me. So if you're going to follow what I did, I basically went like this. And this could be a solution to this differential equation. Now, it's not the only solution. Like if I started over here and just kind of followed the slopes, I get something in a different spot. So it all depends on where you start and how you just kind of follow things. This is not an exact science with these. It is always just sketching it out based on the way the slopes look. So that is what a slope field is. Oh, geez, I didn't want that. Clear all drawings. Okay. And if you want to play around with them some more, and at some point you might want to, again, the link to that is right on the slide. So you can always come back here and check that link out. And you can put in any differential equation you want, just the one I happen to use. Okay, here are four other differential equations I can count. So we're going to try to solve these. And we're just going to do these all together. But just make a note, these are the four that we're going to try to solve. Now to solve these, we want to separate the variables and then try to integrate to get rid of the differential. So let's start with this one. So I have dy dx equals x over 3y. So I'm going to separate the variables, get everything with a y on one side, everything with an x on the other side. So I get 3y times dy equals x times dx. Again, dy is a differential. It's a variable all by itself. Don't separate the d and the y. It's a single thing. I need to go this way. Boom town. All right. Here we go. Now at this point, what I want to do is I want to integrate both sides, because as soon as I put that integral on there, remember integrals are like a two-piece operation. I need the integral symbol and the differential. It's like I want to make a sandwich out of bread. If it's not with bread, then it's not a sandwich. By cubic rule of food, you need structural starch. Point being, now that I have this, now I can do the antiderivative of each side. So if I do that, I get 3/2 y squared equals 1/2 x squared plus c. Now, the first thing I put up here was remember to include a constant of integration. I integrated both sides, but I only have one constant. That might feel bad, but it's okay. The reason is, oh, I didn't look back and check it out. Let me save this real quick. All right. The idea is that if we put a plus c on both sides, that would be okay. But we don't know if they're the same plus c, and there would be different. So then you'd have to give them both subscripts to say they're different c's. So it's easier when you have two integrals like this, just to put one c, one constant integration on one of the sides. Again, you can easily see, pun intended, that there should only be one c. If you have two of them, you subtract one over, and it changes the other c to something else. So you only need a single c of integration. Yeah?
Does it matter which side you're on?
Not at all. I normally put it on the right-hand side just because that's what I do. But yeah, it doesn't matter if it's over here with the y or at the x. All right, here's another one. Dx over dt equals x times t. So for this bad boy, again, we're going to separate the variables. We're going to try to get everything with x on one side, everything with a t on the other side. Generally, the idea with these is that you want to not be dividing by a differential. You want the differentials out of the denominators. So I'm going to divide by x, multiply by dt. And now that I have that set up, I can take the integral of both sides. Again, so what's a little different about the way this is set up here is the dx, it's like dx divided by x. That's the exact same thing as 1 over x times dx. It's just a different way to write it. So now if I find the antiderivative of each side, there we go. And that's done. Again, technically a differential equation is solved as soon as the differentials are gone. So here's another one. I'm going to just give you a minute to kind of think about what the first two steps might be before we do it. Just go to literally open them right there. Oh no, that is also not what I want. Thinking hard. Okay, sorry, Google Drive. Sorry, not sorry. Punk. All right, let's take a look to see how this one's gonna go. Oh, where's the mouse? It disappeared on me. It's there. Now it's here. Okay, so we separate the variables. Get y is on one side, t is on another. We're going to integrate them. Boom. There we go. Again, 1/2 y squared equals 1/3 t cubed plus c. Again, when you do these, as the question was asked earlier, it doesn't matter what side you put the c on. Most of the time, the way these are set up, I just put them on the right side just so I don't have to think about it later. But again, you can put it wherever you'd like. You can get some. All right. Here's another one. So with this one, again, we want to separate the variables. No, I noticed there's only a y. I don't see another t. So there's a couple ways you could approach this one. I'm only going to move the y, and I'm going to leave the 2 where it is. I could bring the 2 with. I'm choosing not to. There's no reason I couldn't bring it with. I'm doing this. I'm only moving the y because I'm trying to keep it as simple as possible whenever I move a variable. I try to leave constants where they are. Basically, I try to do things so that it's advantageous for me. All right, now that I have that, let's integrate. Remember, again, always look at the differential to see what the variable is you're integrating with respect to. In this case, then again, I get natural log of the absolute value of y equals 2t plus c. Boom. So there's a little more to this. So here are each of those 4 differential equations, and here are their solutions to each of those. Again, technically those are all solutions because there's no differential left. A lot of the time, not only do we want to solve the differential equation by getting rid of the differential, we want to explicitly solve it for a particular variable. Usually y, but it depends on the situation. Now, if you're looking at each of these, 3 of the 4 of them have y in them, and we would probably want to solve for them. So if we have a natural log in our solution, or just any logarithm, we usually want to try to get rid of that and just isolate the variable, like explicitly solve for like x or y in this case. So we're going to go through what's it like to explicitly solve for the natural logs here, because there's a couple extra things I want to be super careful about. Because these first two are in this first column, divide by 3, square root, boom, y solve for, you can go from there. There'll be a plus or minus out front, and you need to know an initial condition in order to figure out which way it's going to go. But let's see what happens with this natural log one down here. So let's solve this one for y. Well, the inverse to undo natural log, we're going to exponentiate. Again, everything is going to become an exponent to the base e. Again, I'm picking e because it undoes natural log. So to simplify, I get absolute value of y equals e to the 2t plus c. Now I'm going to rewrite it without the absolute value now, because exponentials are always positive, so I don't need to worry about keeping that y, the absolute value of y. If I didn't have an exponential on that side, that would be a cause for concern, and that's something we'd have to like consider the situations. Okay, we always need to consider the situation, whether it should be there or not, and to take an extra step if we want to remove it. All right, well, at this point, we've solved for y. But this side, we can simplify that a little bit. And in fact, what we're doing to simplify it is we're rewriting it using the laws of exponents. Because remember, when you have like 2 to the 3rd times 2 to the 7th, that's equal to 2 to the 10th because it's 2 to the 3 plus 7. So if I have e to the 2t plus c, I could break that up into e to the 2t times e to the c. Again, that's usually the reverse of what we do with laws of exponents. We usually combine everything rather than break them apart. But for solving differential equations, particularly ones that have logs in them, we like this because we can then turn e to the c into c, a giant C. Now this feels like a giant trick, and it kind of is. So thinking about this, c is some constant, right? It's just some number. I don't know what that number is, but it's just some number. When I have e to the c here, again, it's e to the c. It's e to some number. So really, e to the c is, again, just some number. So e to the c might as well just be a constant all by itself. This is probably the hardest thing to grasp, like why we do that. It's kind of the trickiest thing, I think. But like explaining it as it's just a constant. And if I don't define what that constant is right at the beginning, it can kind of just absorb things as it goes along. And it's kind of blob constant, I like to call it. So you have C. And since that's a constant, I'm just going to bring it out front. Hey, that kind of looks like the thing we started with. Oh, that's right. I had it animated so it would come in. Look at that. It is basically that one of those two equations that we started with. So this is the general solution to the differential equation. The change in y is proportional to y, which is this. A lot of modeling in like more advanced math and advanced science deals with this relationship a lot. I also think about the change in Y is proportional to Y. I think about cooling coffee because, well, coffee, but the hotter coffee is, the faster it cools off. Or like the more caffeine you have in your body, the faster your body eliminates it. That's more of an inverse relationship than a proportional relationship, or a direct proportional. But it's still that idea is that like the more something is, the more it changes. Maybe you could say the bigger the fire, the faster a room heats up. Because I don't know, I'm just thinking about burning in coffees. And burning coffee is terrible. Oh, geez. All right, so this is the general solution to this. If we want a specific solution, we need to know some initial values. So this is also the model we're going to use for exponential growth and decay. Now, a lot of the time with growth and decay, we use like amount times 1/2 to the power of t, because we're implying half-life. But it's not always half-life or double growth or double life. I don't know what the other version would be, but it's something. We're doing good. So here's what each of those things in theory would represent. Again, K is a proportionality constant. In order to figure that out, you'll probably have some initial values and you'll have to solve for K so you can use that value throughout the thing. In the practice, there's some stuff about decaying isotopes, I want to say they are. I'm not sure that's the right word, but I think there's isotopes. And you have to figure out like how much is left after a certain number of years. And that deals with proportionality constant and half-life. And there's some things in there. You have to play around with that a little bit. But basically uses this model. This is the model we're going to use for that. Again, there are multiple models we can use, but this is the model we're going to use for the rest of this class because it's the one that's going to come up the most on the AP test. Hey, this one, we should probably talk about this bad boy. So this equation is called Newton's law of cooling. You could say that it is pretty cool. Yeah, it's so good. So here's a big old statement of what Newton's law of cooling says. And it basically is taking that equation and putting it into words. And it's what I was just talking about with coffee. But B represents the temperature of the body, Q represents the temperature of the surroundings, and T represents time. Again, we can model that in many different ways. Like we modeled Newton's law of cooling several different times last year in pre-calc. Again, literally thinking about coffee because that's what mathematicians and math teachers think about constantly is coffee. So we're always talking about like, how does the coffee changing? And there was that one awesome team test problem with when grandma got run over by a reindeer and we measured the body temperature like a couple different times to try to figure out when she died and was trampled by a reindeer. But except for that one time, it was pretty much always coffee. Now in calculus, using differentials, we can represent it a little bit differently. Again, when you solve that, it still turns out to be the other thing we had. But that's it. And there's your practice. There are some postscript things, but those are mostly just old notes and old versions of the stuff I did up there. I don't even know if it's super helpful, but they're just different ways that I said things in the past. And I think what I have now is better, but if you want some extra things, there are some post credits. And it's 25 minutes in. So on that note, folks, virtually, if you want to stick around and ask questions, please do so. I am going to open up a Jamboard and put it in up here once everyone gets a chance to do that. But otherwise, on that note, have a wonderful day. We'll talk to you later. Virtual folks and in-person folks, you have time to work and you can ask questions, raising hands, and I'll yell at you from across the room. Let me change the name of this to 5.6. I'll leave that up there for just a little while longer, make sure everybody's got that.